Okay. Uh, so, hello everyone. So, welcome to today's live session. So, today's live session is on LTSPICE. Okay. And so, this is an extra session apart from the 12-week session we had for problem solving. So, this is an extra session that is for, so that is going to introduce you to LTSPICE. Okay. So, for the installation and the model part, what we are going to do is we are going to refer to uh, the supplementary material that was provided to us. Okay. So you can go to the SOAM platform. You can go to week one. So there is a section called a supplementary material. Click that. So you will have it will lead you to this portion. So then click on this link, and so this will be the PDF that will. Okay. So we are going to use LT Spice. Okay. So that is a popular freeware simulator. Okay. And so these exercises that are mentioned in the week one supplementary problem, they are beyond the ambit of the certification requirements of NPTEL online course. Okay. But it is good to have a practice with LT Spice. So that can help you to solve uh, any circuit that we came across in the entire duration of our course. Whatever circuits we have come across during our lectures. So you can simulate them. You can do various form of characterization. You can also figure out what will be the output current. And for that, so you just need to click on this link and it will lead you to the LTSpice downloads page. So there you can just select whatever operating system is applicable for you. Just click on that and move ahead, do your installation. Okay. That is the LTSpice part. So once it is installed, so you will have so this is how the LTSpice opening screen looks like. So you can just click on this button here, new schematic, and it will open a schematic window. So first we are going to do, we will first save this file. Okay. So I'm going to save it in, okay, so this live session. Let us, let's say in WordPad, okay, and just save this. Fine. So now there is one more thing that we need to do before we actually start our simulations. Okay, so if you can see, point number 3 tells us that the transistor models of 180 nanometer CMOS process for all devices, it is available in this particular link. So when you click this, it will redirect you to IIT Madras page of Professor Nagendra Krishnapura. Okay, so from here you can pick any technology that you like. So here it is the supplementary material. It is mentioned 180 nanometer. So we will be sticking to the 180 nanometer part for this tutorial session. Okay, so click on this one. Okay, then you can see a bunch of parameters mentioned. So this is basically describing how your what your model parameters are. Right? So you can see VTH, VT naught, CF, PVSAT, and there will be some other parameters here. So you can read more about these parameters from the BSIM 3 version documentation. Okay, so now we need to download this. So what you do is just press Control S in this page, okay, and go to the location that we decided. So it was extra session, LTSpace live session. Okay, save as all files. tsmc018.lib is the file name. Right? Just click on save. Okay, so here just be careful because even after saving as all files, it's saved as .txt. So in that case, what you need to do is just go here and double click and open this. Let's see, what is this? Just delete it. Paste it. File, save as PSUC018 dot LAB. Okay. Now you can see the text file is gone. So, I mean, the type it says is Altium library, but it's basically our .lib file. Okay. So now we have the .lib file. So what we are going to do is, now let us open our LTSPICE. Okay. So after after opening LTSPICE, what we need to do is we need to create symbols or the model libraries that we imported system. So just go to file, sorry, just go to file, new symbol. Okay. So here, draw the PMOS and NMOS. Go to draw line. So first we will start with our PMOS. Okay. So to draw a line, go to the draw tool and you have your line and everything. So this is basically a symbol for your PMOS and NMOS that we are going to take from our TSMC 180 nanometer library. Fine. So yeah, Control C is for copy. So what I'm going to do is just copy this line. Then I want to make a circle. So here you just make a circle. Let's see what that is. Okay. And then what I will do is, so M is for move. So I click on the circle and it will, okay. Okay. Now let us draw all the terminals. Choose line. And next the body term. Okay. So after you are done with, okay, so let me, okay. Then go to file, save as, CMOS. Once that is done, go to edit, add pin or port. Okay. So source gate. So let's write G. Okay. So the netlist order is important here. Okay. So drain gate source body. Okay. So that is the way in which we define an the spice simulators, right? So drain is netlist order one. Gate is netlist order two. Okay. So let's do it accordingly. So drain is netlist order one. So let's mark our drain terminal here. Okay. Then next you can type P or you can go to edit and add here. Okay. So the next is netlist order two, that is our gate. Here, drain gate. Source is netlist order three. Okay. And let us say you want to edit a parameter that you have already placed. Just right click on that parameter and you can see the option. Okay. So here I want to place it like this. Okay. Then you just put another one, drain gate. Later. This is what. This is where I placed them. Once that is done, save this. Now go to edit attributes, edit attributes. So value, the prefix is this is PMOS, right? So just type NP. Okay. And the model file is TSMC 018. Write the value as CMOS. Let's take a test step. Okay. So this is done. Let us try instantiate it in our inverter. So in the inverter schematic, so this is a symbol. Okay. In the inverter schematic, what you need to do is you need to instantiate this symbol. So click on this component. Okay. Here you can see, I think we need to save this properly. It's there. Okay. So you can see. So when I tried to open from the inverter, the PMOS, it was not opening. Probably it was not refreshed. But now you can just go to component, click the CMOS P, and you can see the symbol that we made. It is available here. Just click on this thing. Okay. Now, similarly, we need to make a symbol for our enemies. So what you need to do is again go file, new symbol. Okay. Now you save this first. File save as CMOS N. Okay. So now you draw a similar structure for enemies. Okay. And once it is done, just save it. Again, we will go back to our add pin support. So drain, this is my drain terminal. And next is gate. Next is source. Okay, so this order is important. Okay. So once it is done, you save this, go to edit attributes, edit attributes. Okay. So here prefix will be MN, value will be CMOS N. Okay. And model file will be TSMC 018. Okay. Once that is done, go back to your inverter, go to the components. Okay. So CMOS N is not visible now. What you do is close this, reopen the inverter. Okay. So now check again. So CMOS N is available. Double click on this one. Okay. And so you can zoom in or zoom out by using the mouse scroll button. Okay. So okay, this is how I place it. Now what we are going to do is, so we are ready with our symbols. So what we have done is we have instantiated, we have made two symbols for CMOS N and CMOS P. Okay. And we have downloaded the TSMC 018.lib library, model library. So the parameters of this NMOS transistor and PMOS transistor, it is going to be picked from the library that we have. Okay. And now the first experiment that we are going to do is we are going to perform transient analysis on an inverter. Okay. We want to see whether we are able to functionally get the input output relation of inverter. Okay. So it means if I apply one, I should get a zero output. So press W for wire. Okay. Next the drain terminals. Okay. The body and source we are going to short it. Okay. Okay. The gates will also be shorted. Okay. So this is done. So now what we need is we need voltage source. Click on voltage source. So there is one voltage source. Okay. Now if you want to rotate, Control R is the shortcut to rotate. Let us say I want to place it like this. The second voltage source is for the VDD. Okay. So now just right click on the voltage source. So screen something like this will pop up. So click on advanced. So the input that I want to give is a pulse input. Okay. So V initial, I want to keep it as 0. V on is 1. Okay. It's up to you. You can give 1 or 1.8, anything is fine. T delay, I'll give 0. T rise, I'll give 1 pico. T fall 1 pico. T on, I'll give 10 nano. And the total period, I'll give 21. So this is basically a 50% duty cycle rate. Okay. N cycles, I will say I want to do it in 5 cycles. Okay. So click on. So you can see the entire information of whatever setting you have done is available. So now connect it to the gate tab. Okay. Connect this one to the system. Okay. So once you are done, so now we need to let's display the values 1.8. Right. So now we need to connect the grounds. So you have ground available here. Just put the grounds here, here. Okay. Okay. Now let us label our input and output. So to label input and output, we are going to use this label net option. Click here. So input, I'll name it as VN, type input. Okay. I said click this. Same thing I'll do for the output. And I'll place it like this. Okay. So this is done. So now what we need to do is, so whatever model library that we are using, so we will use this spice directive to call that model library. So .inc space tsmc 018 dot library. Okay. So place this here. Once it is done, so first analysis that we will do is, uh, okay, let me show you the operating point. So this is a very basic analysis, basic operating point. You can just place it here, and after placing, just click on run pause. Okay. So once you click on run pause, you can see. So it will give you the device current information, ID M1. So M1 is your transistor. Okay. So which transistor you need to check that. Okay. So then ID M2 is some value. So the V in is 1.8. Sorry, V in is 0. V out is 1.8. Because so this is only for a DC, right? So but we applied a pulse. So the initial value of the pulse we gave as 0, right? So that is why V in is 0 and V out is 1.8, right? Okay. But this is very basic operating point. So when you do the operating point analysis, you want to do a fixed voltage value. So instead of giving a pulse, what you do is you choose a fixed value. Okay. So now let's say Okay, I want to add a transient analysis because I want to see the functionality of this. To stop time, uh, so the period of the entire pulse we gave as 20 nano, right? So, and it is going to run for 5 cycles. So it means 300 nano. So let us give stop time as 100 nano. Times to start saving the data. So for this, like let us keep it as 1.9, 1 nano. So I'll explain like when this time to start saving data is useful in what situation in the third example that and maximum time step you can keep it to 1 nano. This is not a problem. Just keep it here, keep it like this. And whatever analysis you don't want to be active, so just right click on that and put this symbol. Okay. Once you do that, it will mean, oh, sorry. Okay. Let it be. So what we are going to do is we are going to save it and okay. Now let me use the symbols, rearrange this. Okay. So what I will do is, so you can see when you run the simulation, you will have a probe option available with. I'll click on the input first. Okay. And the input is available too. So I'll press P button to get another pair of input and then I'll click on V out. Okay. So you can see, okay. So here we haven't specified one thing. So the MOSFET's value. Okay. So let us say I want to take length as 0.18 meter and width is 8 meter. Now for the NMOS, 0.18 micro and width is 3 micro. Okay. So I do this, I save this, let me close this window. Okay. Then I perform my analysis again. Okay. Now let us see. This is my VN and this is how my V off is. Okay. You can see the moment we have a high as input, the output is 0. And the moment we have a 0 as input, the output is 1.5. Okay, that is basically your time. So this is how we do the transient simulation. So with this, we can see that this model that we have designed is functioning as an inverter. Okay. And like what are the parameter values that it is taking? So it is taking the values from the TSMC 018.11 that is available with us. Okay. This fine. Okay. So this is the first thing that we do. The next thing that we are going to do is, okay, so we are going to plot the input versus output relationship. Okay. So to do that, let me just close this window. Okay. What I will do is, uh, I call it as GS. So let's just comment that input analysis. This is safe. GS. Type of it is linear. Start value, we will start from 0 and we will stop at 1.8. The increment refers to at what value you want to uh, compute the other parameter. Okay. At what increment of what value. So let us try to compute at 10 milli increment. This one, basically. Then yeah, actually I gave that. Okay. Yeah. So, okay, so if we want to observe what is the current, so you can see for voltage we have this red probe. For current, we will get this circle now. Okay. Let's click on this. Okay. So this is the current versus VGS here. Okay. So we are varying the actually VGS of this inverter, and we are plotting what is the current, the drain current. This thing. So we can see that around uh, zero point 0.8 or something, we are getting the maximum current. Okay. So let us see what is the V out. Okay. So this is the V out versus V in. Okay. So the left side, it shows our V out scale. The right side is the current, the change in current. And the bottom one is the change in VGS. Okay. So the peak occurs at exactly the midpoint. The reason is at that point, both the transistors are in saturation. So when both the transistors are in saturation, you'll get the maximum current. Okay. So that was about inverter part. Okay. Now let us check a common source amplifier. Okay. Sorry. Now let us see the RC circuit. Okay. So this is nothing but a simple RC circuit. So I'm going to do the small signal analysis of this RC circuit. Okay. So in that one, we will use, you go to AC, just click on AC analysis, choose the type of switch as per your requirement. Okay, number of points per decade, it means how many number of points you want to compute per decade. Start frequency, you can choose anything of your choice. I have chosen zero point 0.1 hertz. And stop frequency, I have chosen 100 mega. Okay. Then similarly, like we did in the previous case, uh, you can put your pins, put your R1 and C1, then just okay. So this gives you your magnitude as well as phase response. Okay. We can see we have the phase response of a low pass filter because this will not be considered. So from here, you can figure out what is the 3 dB and so similarly for whatever experiments that we have seen, right? Like so today we will uh, yeah. So whatever things are given here, you can try those things out. We will try the PTAT one out now. Okay? But before going to the PTAT, I'll show the common source amplifier first. Okay, so for the common source amplifier, what I have done is I have used the same CMOS N that we designed few minutes back. Okay, and that thing I have instantiated it here. Okay, and after instantiating, I just connected. I mean, this is a very basic connection that I have done. I have connected an RD uh, across the drain and voltage, and I have used it for 1.2 volt and I'm running a transient simulation. So here for the DC biasing, what I have done, there is a DC offset option that is present for the sinusoid. Okay. That I have applied, and the amplitude of the input signal I have given as I have kept at 1 frequency. I have given 1 kilohertz. Then that's all for the source part. Then I have used a decoupling cap. So this is to block the DC component because you can see that whatever output we are going to have, it is basically going to ride upon our DC signal. So I don't want that, so I'm using a coupling capacitor, decoupling capacitor, and I'm using a load, so load of 100 kilo. And yeah, so that's all here. And you need to include the TSMC 018 clip. Yes, just run this. So you can see. So we have our. Yeah. So what I'm plotting it. Okay. So I'm. Okay. So the V out, because we have blocked the DC component using our CN, okay, we have the value at 0. But the V in is actually riding on top of 500 millivolt of DC bias that we applied. So in the plot, what I do is, so you can go to the plot, whatever is present here, just right click, okay, and enter the algebraic expression that you want to get. So what I did V of V in minus 500 millivolt. So that the DC shift is equal. Okay, and I just plotted it. Otherwise, if you don't do that, so if you directly plot it, so you can see that directly. So you can see, otherwise it would have been 500 millivolt. Okay, then you can see that this is actually performing our amplification because you can see the input sinusoid is uh, between minus zero point 0.9 millivolt to zero point 0.9 millivolt, but the output is from minus 4.5 millivolt to 4.5 millivolt. Okay. So it has a gain of roughly 50, right? So 4.5 by point 0.9, sorry, 5. Right. Okay. So that was our common source amplifier. Similarly, you can explore a bunch of amplifier topologies. Okay. So then there is one other thing. Yeah. So you can so while evaluating, like you need to ensure that your transistor is in saturation region, right? So there you click on the dot op. Okay. So the operating point analysis, you can see what is your VGS, what is your VDS. Okay. And from there, you need to ensure that your VGS minus VTH is less than your VDS, such that it operates in saturation. Only then it will behave as an amplifier. Okay, so that was our common source amplifier. So the next part is related to H bridge. So, okay. So the H bridge doubler that we have seen, and so this is how our H bridge doubler looked like. Right? So we had four MOSFETs connected in this fashion. Okay, and the top left and bottom right MOSFETs are connected to phase phi 2. The bottom left and top right MOSFETs are connected to phase phi 1. And the input is applied at the common drain of the top two MOSFETs. Okay. So V3 is our input. That is of 20 millivolt in this case. Okay. And the V out is taken from the source terminal of the bottom right MOSFET. Okay. And phi 1 and phi 2 are the phase, the clocks that are applied. And C1 is the capacitor that I have chosen. So capacitor, you can pick it from here and place it here. Okay. So, okay. And phi 1, okay. So I open this. Phi 1, what I have done is the V initial, I have kept it as 0. The V on is 1. And the T on, I have kept it as 10 nano and T period of 20 nano. Okay. So for V2, what I have done is V initial is 1 and V on is 0. So complete opposite of what phi 2 was. Okay. So this was kept just to ensure that we have non-overlapping clocks. So usually you will have a single clock. From there, you can get the two non-overlapping clock phases by using something that looks like a flip that we have seen in the course. Right? But for this simulation, what I have done is I have created separate phi 1 and phi 2 and I have applied it to the signal. Okay, let us do the simulation and see. Okay, yeah, so there is an interesting thing in the transient part. So as I mentioned in the starting, right? So what I'm doing here is so we have an option. When do you want to start to save the data? Okay. So what I'm doing here is I'm having a zero point 0.4 nanosecond offset. Only after which I start saving the data. Okay. So the reason is initially I can see. So when I'll plot, I'll show that there is a small overshoot kind of thing. Only then after that it uh, comes to its stable position. Right. So for that reason, I just don't want to see the overshoot. So I just put it at 0.4. I do play. Okay. So this is my input. Okay. At 20 millivolt, and this is my out. So let me get it right here. This is my out. You can see the output is close to. Uh, so you can place your cursor. So C is for cursor, and you can see the vertical value. It says that 39.999 something. So that is basically doubling our voltage, whatever we have. Okay, the same thing you can do to figure out at what point it stabilizes completely. Okay. So you can move this one. You can see at around 39.3 picosecond, it stabilizes. Okay. So that you can use. Now let us modify this value to, let's say, 12, 11 millions. Okay. So what we are expecting is the value at V out, it should be 22 million. Okay. Let us see. Right? It is going to 22. 21.999. Okay. So if we would not have given the time skip for saving the transistors, let us say I would have given 0. So then you can see, it would have been difficult for us to observe the actual this thing because initial we have a sharp peak. So unless this transient settles, we won't be able to. see the actual voltage value, right? And for that reason, I gave I gave a skip of 0.4 or 0.5 also you can. And then I got it. Now you can see we have a clean signal. 22. So similarly, in the same way, you can try it for um, your H bridge half, like the circuit that we performed, half an operation, or even the triplet that we saw. Okay. Or if you want to experiment further, so you can see in the X bridge part. So we were explained a complete circuit, right, which has a bunch of programmable options to generate um, 2 by 3, 1 by 4, 3 by 4, and something. So you can use this to experiment. So usually my work involves uh, cadence, but it is fine. But that is paid tool, right? So I mean, uh, access to cadence is very limited. So instead, what you can do is you can uh, do whatever simulations you want. So this is also good enough, and you can pick the model libraries like as we were discussing initially from this link that was provided. So we just did it for TSMC 180 nanometer. So you can pick. So there are bunch. So we have 16 nanometer high performance predictive technology as well. Okay. So I mean, you can't design something that is actually fit for paper, but for academic purpose. So these things are good enough. So you can pick anything of your choice, and based on that, just give the names to your MOSFET and everything, and then you can perform your simulation. Okay, this was the first bridge. Okay. So similarly, uh, yeah, so similarly, let us now move to the first question. Okay. So in the first question, what it shows is, so we have a p-type voltage reference, and what is asked is assume that Q1 and Q2 are identical. Basically, so we have a bunch of BJTs available in the inbuilt toolbox. It says that IC1 we have to pick as 10 microamps, IC2 as 1 micro. Plot BBE1, BBE2, BBE with respect to temperature, ranging from minus 40 degrees Celsius to 120 degrees Celsius. And we are supposed to figure out what are the temperature coefficient of the three voltages. Okay. And after plotting, we have to comment on the nonlinearity if there is. Right? So this is the first question. Okay. So let us see. Okay. Basically, this is the setup that we were supposed to do. So for the BJTs, what I did is I picked I think it was PNP. Yeah, this is PNP. Just pick PNP, and then you can right click, pick new transistor, then pick any transistor of your choice. So what I have picked is 2N2907. That is from NXT. Click on OK. And similarly, so okay, so I'll tell you one code shortcut. So after you press M, if you click on the MOSFET, you can move it. So while moving, you can press Control E to mirror it or Control R to rotate it. So these are a bunch of keyboard shortcuts that are present. So if you want to know more about those keyboard shortcuts, you can click on Help Keyboard Shortcuts. Okay. So you have the complete appendix of all the keyboard shortcuts that are available. Okay. And so keyboard shortcuts, they behave differently. So if you would have seen when we were using the waveform, I pressed C for the cursor. But if I do the same thing in schematic, it opens up a capacitor. So for a different region, we have a different keyboard shortcuts. If you want to edit anything, you can do that using the edit keyboard shortcuts. Okay. So yeah, and then you can just so you can see the dots, right? So you can make them visible, invisible using the Control G. Okay. So coming back to our problem statement. So what I did, I just got the two transistors. Then I needed to place current sources. So I have, if I type current, I can get the current sources here. Place the current source, one current source here, one current source here. Apply the value that is given to you. So I applied, so if you right click, you can see I have applied 10 micro and 1 micro here. Okay. And I just labeled the nodes. I did not put any input or output. I just clicked on net, and you can put anything. Let's say XY. Put type as none. Okay. And you can just label the node. Similarly, I just labeled it as A and labeled it as B. In our case, so A corresponds to VBE1, B corresponds to VBE2, and we are supposed to find out A minus B. Okay. And before that, we need to do a temperature sweep. So for temperature sweep, what I did, so we just click on configure analysis. You have DC sweep option. So just name the variable as temp. Okay. And type of sweep as linear. It's up to you what kind of sweep you want. I chose a linear sweep. Start value I gave from minus 40 and 120 and increment of 1 degree Celsius. Okay. Okay. Now, so what I have done is I have commented this out. Okay. Let me show you something. If I have both of them here, you can see there is an error message. Cannot have dot step for a temperature and dot sweep for temperature at the same time. So here, what we get to know is, so this recognized, the simulator recognized that we are planning for a temperature sweep. So writing PEMP is good enough. Okay. But we can't have both of them at the same time. So what I do is, I just place semicolon at the beginning to disable this particular simulation. Okay. Then I click on save. Okay. Then now we need to plot the voltage at A, okay, the voltage at B, okay, and the voltage at A minus B. So what I will do is VA minus, okay. So this is how we are going to do the plotting. So these are the three plots that we have required. Okay. Now let us see. So what you can do is, okay. So this will basically give you the derivative of the temperature. Okay. Then so if let's say from here you want to label something, you can just type two, and let us say you want to label it as beta. Any let's try and just place it like this. So so you can see, so the output is actually is two. So I have only plotted VA and VA minus VB. Yeah. So you can see that for the PFAT case, as the temperature increases, so this plot also goes on increase. That is the behavior of our proportional to absolute temperatures uh, that we expect. That we expect, right? So similarly, you can construct for CTAT, and you can also construct for your complete BGR that is present. Yeah. And you can pick an ideal op amp to in your simulation. So your ideal op amp is okay. For the ideal op amp, you can go here. You can see if we have many versions of amps. We have universal op amp. Okay. So based on so this is like uh, this is the ideal single pole operational amplifier. You can pick that, or you can pick any op amp of your choice, and you can perform those experiments. Okay. Then so there are many other things that you can also do. You can introduce a voltage offset. Okay. So how will you introduce a voltage offset? So what you can do, one terminal, you can connect a DC source with DC voltage as let's say 10 millivolt and see how it is affecting your output. Okay. Similarly, you can have a differential amplifier, okay, with one terminal connected to Vref plus delta V and other terminal connected to Vref and see how the output is. Okay. Then you can perform an experiment by having uh, okay. So in this case, the switches that I implemented for the space was using MOSFETs. So if you want, you can use ideal switches as well. Okay. So SW is the one that will give you the switches. So you have a controller and then you have your input and output ports of your switches. Okay. So using that, you will be able to get your ideal switch. So you can also model a sample and hold. You can also try to simulate an ADC and bunch of other things. And because switching is there, so you can also try out the auto zeroing experiment that was mentioned in the class. So auto zeroing, chopping, and how it gets rid of the offset. So you can introduce the offset. You can see like whether the auto zeroing with auto zeroing enable, whether you are able to see that the offset is uh, present, and with auto zeroing enable, whether the offset gets cancelled. Okay. So these are the bunch of experiments that you can perform. And so LTSPICE has a huge forum, I mean, a huge community. So you can feel free to ask whatever doubts you have on that forum as well. Okay. And so you can get a good idea of how things work using it. So, oh, okay. So there is a question. Okay. Actually, the questions are not appearing there. Uh, how you have plotted V out versus V in. Oh, okay. Yeah. So the V out versus V in part. Uh, I think this is for the inverter. Let me open it again. This was our inverter. So what I did is, so I chose the V in as a variable, okay, named it as VGS, and gradually went on incrementing in steps of 10 millivolt the V gate, the gate voltage of this inverter. Okay, and uh, let's run it. Okay, so this is our inverter. So what I do is, so anything that I'm going to plot is going to be the x-axis is going to be VGS because that is the thing that is being varied, and whatever I select is going to be the one that is going to be objected. So I clicked on V out, and this is how I obtain uh, V out versus V in. Okay. Then there are bunch of other things that also can be done. Okay. Let us say that. Uh, I just plotted the current. Yes. So what I will do is, I put this on my word. I will do the answer. Answer is, let me put this. This is the input and output that we get. So let us say that this is the input. This input signal, which I want to take the FFT. Yes. Okay. Then we can get the FFT, whatever signal we have. So as I mentioned, right? So you can have some sort of an ADC design with this, okay? And then from here you can get the FFT, and that FFT, and you can get your required harmonics, okay, and your fundamental. Like in this case, if I place the cursor here, place it here, okay. So the fundamental, it comes around 1 kilohertz. That is not signal of interest. Okay. So similarly, you can use this to characterize whatever ADC you have designed, and based on that, you can see where the harmonics are present and what is the harmonic power and other components. Um, so okay, so what I was trying to show is, okay, so let us say I have the inverter, okay, and I just applied a sine wave. So this is a different form of analysis. Okay. And let us say I only take the input present here. Okay. So this input, I want to see the FFT of that. Input to view, and in view you have an option called as FFT. Click on that, choose the number of data points, sample time, and the number of points. And other thing, if you want to use any window function, there are bunch of window functions that are available. Let us say I choose Bartlett, then press O. And you can see we have the complete picture of this, right? So here you can see my fundamental, it appears here. That is roughly at 1 kilohertz, right? So using this, you can do the characterization for an ADC that you have designed. Okay, and you can also see where your ADC's harmonics are lying. Right? Then there are bunch of other options also that available in LTSPICE. If you want to annotate anything, let us say I annotate this as sign. You can just hit here. The same thing can be done here as well. You can just place a text or whatever comment you want. So you can enable the grid settings to observe the value precisely. Okay. Now let us say you have done some simulation and you want to export the data. So there is an option called as export data. Let's click this one. Which files you want to export, you can just choose it here and then click on OK. If I click on OK, yeah. So this is the location where it is. So and false. Yeah, yes. But it is mentioned that it is in continuous conduction mode. Not, no. It should be V in minus V out by N by equal. Not equal at V not equal to 1.1 point 0. So, did you ask for a clarification to the individual who has prepared this question? So, usually, whenever we have a, let us say we want to challenge the solution that is given, right? In previous NPTEL courses, what I used to suggest the student is go to the Swayam platform, and there in the Q&A section, right, you can ask it to the uh, NPTEL team itself. And usually, if they see that the answer that is coming out is not correct, and if you have given enough reasons, then they kind of consider, like, they can consider that, I mean, whether grace mark has to be given for that. Otherwise, yeah. So better ask them for a I mean, solution that is possible. So yeah, so just save it. Yeah, so this is the location. So PhD practice. I'll save it in a other file. Save it in live session. It's a test.txt. Save it in live session. Test.txt. This is where we have saved our file, and this is the complete data. Okay. So one side is one axis. Okay, so VGS is this one, the first column. V out is the next column. VN001 is the third column. IS is the last one. Similarly, you can perform bunch of analysis, take the data out, do whatever post processing you want to do with the data. I mean, as I showed, right, like you can just take the FFT. So you can view, take the, so let us say this FFT, whatever is coming out of this is the FFT, right? So, like whatever FFT you have taken, you want to you have some sort of a classifier or some sort of something that takes other valuable information out of FFT that is not present in the tool. So many a times we do that. So let us say we want to get the SNDR or effective number of bits rate. So we take the FFT data, be it in Cadence, be it in LTSPICE. You put it in MATLAB, you write some sort of a code to get effective number of bits out of that, or you want to get the noise floor out of that. So those things also you can do. Here also you can just take the FFT data as export data as TX. Okay. The same thing you can do. Okay. So those are the several features that are available in LTSPICE. And it's a good thing available for uh, you know, people who do not have access to the commercial tools like Cadence or Synopsys. And it's actually very good. Okay. So I think, yeah, that brings us to the end of today's session. If there is any question regarding LT slice or anything regarding whatever we have covered today, so please let me know. And I think you had a question. So how you plotted V out versus V in, right? I'll show that. So to the inverter, I think. Okay, so this was my inverter. So basically, what I do is I just choose analysis, DCC, uh, which name it as VCS. Type of start value is 0, value is 8, 10 milli. I just want to disable this source. So, so whatever I want to plot, so already it is going to be with respect to VGS. I just select the V out. Okay. Once you select the V out, you can get V out versus V in. Is that fine? Okay. So is there any other question that you want to ask? And so the next session will be our last session on 12th. So before that, if you want to ask any other question, you can let me know. So I have noted down like you wanted me to cover one question on current sensing methods and buck boost converter that I will cover in Saturday's session. Uh, is there anything in addition to that which you want me to cover? I can cover. If not, then I think we can wrap up today's session. This recording will be available on the YouTube channel. Yeah, and you can try out the other problems that are given here. So this is actually very, these are actually good things that you can practice. 1.2 volt, sub 1 volt band gap reference. Those things are given. And as I already showed in today's session, some questions on compensation as well. So can you be a bit more specific on which compensation? Dominant full, type 1, type 2. Oh, okay, okay. Yeah, sure. But the thing is, for type 1, type 2 compensation, right? So it is difficult to frame a question. So the thing is, unless I actually do it myself and plus simulate it, I can't know the answer, right? So that is why type 1, type 2 compensation, it takes a bit of. So, anyways, I'll try to see if I can form a question because I have to again see that whatever circuit, because it is architecture based mostly. So I have to check if the circuit that I have come up with is actually stable and it is going to work or not. So it's a bit tricky, but let me see. If I can come up with something, I will. Okay. So if there are no further questions, we will wrap up today's session. Yes. So thanks for joining.